How many have done it? Not all of them. Have you tried to do it? At least some of it. Okay. For those who did, how many courses you tried to solve? All right.
I tried to solve about 20 to 50.
Okay, that's a very good number.
I spent on the first question I did around 10 of those.
Okay. What about the rest of you? Didn't do anything? Jason? 2. Better than 0. So it's good. So the others, you haven't tried to solve the course yet? Remember, we do have a midterm test, right? It's not a free ride all the way to the end. Just to remind you, right? Don't take it like a free ride all the way to the end. When you're a few days away from test, then you started doing this, that could be too late, in my opinion. Okay, that will be too late. So this particular homework, there are 2 problems. For the first problem, I think the first 10 queries for problem 1 is fairly straightforward. You should be able to solve them in less than a few minutes of time. And plus, the database itself is small, which give you a good practice forum where you can take this approach of try and error and fix and refine and try again. Because the database is small, whatever you type, you will be able to get results back. Which is not the case for problem 2. The reason I set up problem 2 is, at least I know you know that there are 2 problems, that they are connecting to 2 different databases. Okay. The problem with the second problem is that the database is large. It's not huge. It's only a few million records. In today's standard, that's still a small database. But in our class, at least compared to the first database, it is huge. So what's the problem with that? The problem is, if you are not careful in the SQL statement you write, it may take a long time to write. And I will show you one case, I think. Basically, remember what I said about SQL, which we're going to talk about this in detail later on. You try to avoid using nested block. The reason is this will be expensive. Part of the reason is Query Optimizer cannot do a good job in optimizing nested blocks. Okay? In typical Query Optimizer, each block is optimized independently. So it's not able to figure out ways to optimize these queries if you put them into nested blocks. So if you try this on problem 2, you know what I'm saying. So oftentimes, if you write a complex nested block query on the second database, it will take a long time to execute. Another observation. Don't be afraid of using join, especially for equal join. Especially for equal join. Why? Later on, we will, once we learn enough about the database kernel, you will know that equal join actually is very efficient, and database is very effective in optimizing equality joins, and they can typically be done fairly efficient. Okay. I think I have one example for that. So let me just go over that together with you. I will do a more detailed review on Tuesday's class. On Tuesday's class, we will have quiz number 1. Okay, we will do in class. We will do a quiz for about 20-some minutes. I will test you on relational algebra and SQL. Okay, what I will do is I'm not going to grade the quiz, but immediately after the quiz, I will go over the solution. And if yours are different from solution, feel free to raise your hand, let us know, and we can do diagnose on the fly for you. In the case when you are not sure whether it's wrong or right, if you know for sure it's wrong, it's right, then there's no point of discussing that further. But in the case when you're not sure about your solution, you should let us know and we can go over this on the fly together. Okay? That's a good way to kind of test yourself whether you can do this or not, because that's pretty much the similar type of problem you will see in your midterm test. If you feel comfortable solving the quiz problem, then you should do pretty well in midterm test. If you have a hard time in solving those quiz problems, that's an alarm you should pay attention to. You should definitely pay attention to that. Okay? Because midterm, if you are not able to do well in quiz, then most likely you won't be able to do well in midterm test either. Okay? That's let's look at this particular query. So I use this as an example because this is a web query where both TAs, they were in my office and said, okay, this query takes very long time to finish. Is there another way to do it so that it's more efficient and we can finish it in a reasonable amount of time? Okay, so I use this as a particular example to demonstrate this point. Let's see how it looks. Okay. Can you see this now? You can see I have my SQL open. I just use this. Okay. First, let's look at this problem itself. Okay. So problem 2 is the DBLP database. This is a real database, by the way. So if you don't know DBLP, just Google it. It's the largest, one of the largest publication repository that's available on the web. You can look at a particular person's publication from here. For example, if you look at my publication. That will give you all the publication I have over different years. Okay, and it also give you. You can also look at the publication from a particular conference. That shows you all the publication from that conference. Do you see that? And this particular database we have. So how did I get that? I used the DBLP download website. It gives you the DTD and XML files that contain all the source data. Of course, it's in XML. XML is something we will discuss briefly if we have time. But just remember, XML is also structured. It's just a different way of presenting structures, capturing structures within data. So just like in relational database, we have schema. In XML, we have something called DTD. To describe the structure within the data. It's a hierarchical structure. It's kind of like a tree structure. You define like each node expect what type, and each node has what kind of children nodes. You specify that in DTD. Then the XML file itself is an instance conforming to that DTD. You follow me? So with the DTD, you can already write a parser. Then when you supply an actual instance of XML file, the parser will be able to extract data out and convert to whatever format you want to. In this particular case, I use the parser on my repository. So one of them is yeah. So this is pathway. If you're interested, you can download this. This is one of the public repository I have over there. So so we pass this and we dump this into our database server. Okay, so it's a real database. Okay, with all the DB records. We have, I think, millions of papers, maybe even close to 10 million of papers, and there are citations and author and conference and so on and so forth. Okay? So that's the schema. This tells you which author is a co-author of which paper. So obviously each paper may have multiple authors, but in this case, we separate them out. So if a paper has 4 authors, that will give you 4 records in the author table with the same paper key but different author names. Citation tells you which paper cite which paper. And for the record, this particular table is not complete. It's not complete. There's some bug in the parser, I believe. It only shows a partial citation relationship among the paper record we have. You follow me? And the conference has a key, name of the conference details, like where the conference is at and so on and so forth. The paper tells you the title of the paper, the year it was published, and in which conference. This is essentially the conference key, by the way. It's the foreign key on this paper. Okay? You follow me? You all follow me? One particular query that the TAs came to me, I think it's this one? No. All the this one, total number of Six Sigma? No, which one?
Last one.
Last one. What was the query I did in my office?
First one.
The first one. Okay, let's go with the first one. The name of author with the most number of papers in Sigma and number of paths he or she has in Sigma. Sigma is the top database conference in the field. The full name is ACM, Special Interest Group on the Management of Data. So it's an annual technical conference organized by ACM, which is the top database conference, right? So we are basically interested at finding the author who published the most with regard to all Sigma conferences. Do you follow me? Okay, how do you do this? Server down. Okay. So the first thing you want to do is figure out what are the Sigma conferences. And this itself is a little bit tricky because we have Sigma conference. We also have workshop attached with Sigma that has a keyword Sigma. So if you simply do a select from conference where name like percentage Sigma, percentage N, that will return not only the Sigma conference itself, but also the workshop attached with the Sigma conference. Let me show that using the database here. So first of all, you describe the conference table. So obviously you are looking for the conference with the name includes this keyword Sigma, right? So you may attempt to do something like, so let's say we only care about the conference key and name without the detail, okay? And this is what I mean. And what do you get, right? you got so these are okay, but you got something like which one has the workshop? So you got things like this. Do you know this? These are not the signal conference itself, but different kind of workshop or small group discussion that are attached to the signal conference. You see that? So how do we get rid of that? You notice that this will be a strong indication that it's actually the signal conference. So there's a word in between signal international conference. But that will not be good enough because if you try to do that, so you may think about, okay, let me do you do this, you find all the signal conference in the 80s, 70s, and 90s. You do not have any signal conference after 2000. Do you follow me? So you can try a different trick, which is, okay, let's get rid of international. See what do we get. Now you get either signal conference or signal international conference, and if you put out also the conference key, let's say we only look at the conference key without the name. Now you see you get what you want. Okay, all the way from 70 to the 2000, all series of these conferences are being returned. Do you follow me? So you solve the first challenge, which is how do you define the signal conference to find all of it? Nothing more, nothing less. The next thing is to look at the query itself. The name of author with most number of papers in sigma and the number of pubs he or she has. So how do you go about solving this? So you have paper key, right? And in paper table you have the conference key.
Do a join.
You do a join between what?
On the paper. Yeah, the paper key.
You join a okay. Obviously you need to involve author and paper and the conference, because that's where you can specify the signal conference. Where in the paper table, this must equal to the conference key from the conference table to make sure it's talks about the same conference. You follow me? And author equal to this. Do you follow me? Make sure you talk about the same paper. And then you enforce using the condition we just figured out. That you are only looking for the signal conferences, not other conferences. Do you follow me? Okay. Right? by author name, right? Order by count. The number of papers that author has. And you're looking for top one, right? You can use a same that we didn't discuss in class, but with a little bit Google and overstack, you can figure this out. There's a keyword called limit. And you make sure this order by this count is descending. Let's say we not only look for top one, we look for top 10 authors. Top 10 obviously give you top one. You follow me?
Can you write group or you have to write group by?
You have to write group by. That will tell. Okay? Right? What do you think? Well, semantically speaking, this is the right syntax to write. So something's wrong. Click on conference. Oh, I had a tab over there. Is it right? C-O-N-F-E-R-E-N-C-E. Huh?
And the C dot name, is that a lowercase c?
No, that's okay.
The case was certainly
Empty set, that's weird.
You are matching p.conference with c.conference key. Conference is the name of the
Conference is the name, not
yeah,
okay.
not key.
All right, got it. So conference is the name, not the conference key. Okay, got it. So in that case, we don't even have to use the conference table at all, right?
Yeah.
We simply do simply do this. You follow me? The conference is the name of the conference, not the key. So will this work? Well, semantically speaking, this is right. So if you write this in your midterm test as a solution, you get points, right? You get full points. But in practice, on this particular database, you write a query like this, it's not going to work. It's not going to work. The reason is this paper table and this author table both are huge. If I'm not wrong, I think the author table is like 4 million records in it. 4-point-some million records in it. The paper table
1.2.
1.2 million. So it's like 1 million something. So you're drawing between 4 million and 1.some millions. It will take a long time. Okay, even though drawing is efficient and effective, but on this particular database, we do not have any indexing structure, which is something we're going to talk about fairly soon. It doesn't have indexing support, so this will take a long time to execute.
I was just going to ask if the cross product was a problem between A and B.
If you think about the conceptual way of evaluating SQL query, if you go with the conceptual evaluation, yes, you you produce the cross product, apply the wire condition, including the join and all that, then print out the final output. And if you do that, there's no way you can finish this work. You have 4 million crossbar with 1 million. How big is that? Think about it. So it's, let's do it, man. That's 4,000 billion, right? Am I right? 4,000 billion records. 4,000 billion records. So let me terminate this. Okay? It's not gonna finish. So let's convince you it's 1.6 million. It's actually more, right? So it's 5 million. So it's 8,000 billion. You're looking at. Obviously, but database kernel will not do a cross product between the two. How exactly does the kernel do it? We will talk about this fairly soon. Right? So stay tuned. But without any indexing support, can we still finish this query somehow? Can we still finish this query and get the results we want? Well, the trick is you want to reduce the size of the table that participates in the join. Oh, by the way, you can also try to do this query using nested blocks, and it will also take forever.
So we only look at the authors that have published anything at all and stick on.
But from the author table, there's no way you can do any filtering on the author table because it only has author name and paper key. So there's no way you can filter that in the first step. But you do, however, can filter out those papers that are not from Sigmund, and only use the remaining papers to do the join. Do you follow me? What I mean is the following. In fact, you don't even have to do distinct count. I will explain that in a minute. Count. Okay? You follow me? Okay?
Could you increase the font size a little bit?
Sure.
Thanks.
Better?
Yeah.
So what I'm doing now is to, instead of join author with paper, I filter the paper table first. So that now it only contains papers that are indeed from the Sigmund conference, one of the Sigmund conferences. Then I join them together. And if you want to be let's see how long this takes. how long this will take, roughly? Remember? A minute? Something like that?
I think this will take a long time because we are taking whole author table.
Full author table.
We took subset of author table that day.
If you what?
We took subset of author table based on sigmod, like paper key.
Okay. So this will might still take a long time. So let me cancel this and let's do even better. So from author table, there's another trick you can do, which is under paper key, the sigma paper will have a keyword sigma, but not only those are sigma papers, because you may have additional workshop and discussion and things like that also has sigma, right? But at least that will give us some pruning. And then we further join with only those from the sigma papers. You follow me? So, what I'm saying is, in sigma, in papers, this is small case letter, I believe. And you can also do some optimization here. You don't have to put out everything. All you need is just need paper key. Do you follow me?
Do you need to do T1 dot paper key in your first nested query?
T1.
So let's start from author where T1 dot paper key.
Oh, no, you don't have to.
Okay.
In this case. Because T1 is to denote the whole thing rather than,
Or I'm sorry, T, not T1.
you mean here?
Yes, let's start from author where.
Oh, no, because this, if you think about this paper key, is still part of author.
Oh, okay.
T1 is to denote the output of this. Let's try to do this. Hopefully this time it will finish.
Is there an upper limit of how long we should wait before we think about changing?
Well, I will argue for this database, give it a minute. But I can terminate earlier than a minute because the TAs tried, it didn't work. So I just want to run through the process. Guys, results back. Do you see the magic of optimizing your queries? Okay? So I'm just using this one example to motivate the importance of keyword optimization. By the way, Michael Stonebaker is the Turing Award winner this year. Okay? And he does database research, by the way. And he won the Turing Award for many, many contributions, of course, outstanding contributions. One of the things he did is keyword optimization and transactions. Okay? Both of the topics we will touch based on later on. Okay? And David DeWitt is another very famous guy. There's so famous, there's a law made after his name called DeWitt clause. You guys can Google this. DeWitt clause. Michael Franklin Raghu is the author of our textbook. Michael Franklin is the director of the PMP Lab at Berkeley. If you don't know what PMP Lab is, you might know Spark and a bunch of other really cool open source projects. It's all done by PMP Lab, directed by Michael Franklin. Hector is author of our second textbook, the complementary reading, a co-author of that book. Yes.
Yeah. So in this query, like we filtered out based on paper key, like sigmod is just based on the observation of the data. So when the data is so used, then how do we assure that?
Very good point. It is based on the observation of the data. So if data doesn't give you that, then obviously you cannot apply filtering like this. So that gives you a general idea in optimizing your query, which is you need to look at your data and look at the query you can write. It's a combination of the two. If you simply rely on the query optimizer inside a database engine, oftentimes it will not work as effective as if you make some observation on your data and go from there. And the observation of your data, speaking of which, this is not entirely quote-unquote safe. If I observe that's what you're doing, I may insert another record that's indeed from Sigmod, but the conference key, I purposely do not use the Sigmod keyword in it. Then this trick will not work, right? So how do you solve that problem? Well, that goes back to what we didn't discuss in this class, which is you want to enforce certain constraint on your database, such as the conference key must have a particular keyword from that conference. Like Sigmod is known as Sigmod, so you must use this keyword, reserved keyword in the conference key. And that's something you can express using functional dependencies, which we didn't discuss in this class. But if you took my undergrad David class, you know what I'm talking about.
If you run the same query again, will the kernel have the results in its cache?
Let's try it. So it took 13.86 seconds just now. If not any of you are using the server now, the cache should still be hot. Well, not much better. Not much better. So you may want to know why that's the case. The answer is I don't know. It really depends on the particular implementation of MySQL. I will expect that it will be faster because you're running the same query again. Right? You're running exactly the same query again, and a lot of things should be cached. But I think one reason is, let's check. I think I know why. Let me just check it really quick.
Could the intermediate queries be just so big that they kick out the cache, so you just have bad?
No, it's not quite the contrary because the data is so small. Let me show you why. Okay, let's do a top. Let's fire up this query. So obviously nobody is using CPU and memory at this moment, right? Let's fire up. Can you see what's going on? Fire up this query. The CPU gets super busy. What do you notice though? In other words, this particular query is CPU is and cache is not bottleneck. So even if they have cached the data, unless they cache the final results, and the cache is smart enough to realize, oh, this is the identical query, I can just return it. But it cannot be sure because database might have been updated between two queries. So it cannot do that for certain, right? So one way to, one potential place this can get speed up is your table is so huge that I have cached some of the base table record in the cache. And so when I ask for those pages, by the discussion we just had last lecture, I'm not paying these IOs anymore. However, as clearly from this example, you can tell the bottleneck is not the IO, the bottleneck is the CPU. So even if there is good caching going on over there, it doesn't really help you reduce the work cost. You follow me? So, if you guys one day become a database administrator, this is the type of thing you need to be good at. Right? Like to figure out how to write efficient, effective queries and to configure your database in a way that it is efficient. One thing I mentioned is we do not have any index on these tables. Let me just convince you that's the case. As you can see, there are no index on this table. Similarly, for paper, there are no index on the table. There's no index. If there is an index, the table statement will show B index or hash attached to that table. Which you may wonder what I'm talking about, but we will come to index discussion fairly soon. If not today, next week. And then you know what I'm talking about. Okay, so I don't want to spend more time on this than I have done, but I hope that this particular example has motivated the curiosity to the kernels and the core optimizations, and the importance of core optimization, of course. And of course, what we have just done is kind of like we are manually doing core optimization, right? What you really hope to be happening is the database kernel do this automatically for you. Because after all, what I claim in the beginning of the lecture, beginning of semester, a database is you tell database what you want, not how to do it. But what we just did is not only what, but we are playing with the how part as well. If the database is so smart, so automatic, I should not worry about the how part at all, right? So, in order to understand those intriguing questions, we need to continue our journey on the kernels. Okay? So let's move back to the lecture here. All right. We talk about this, talk about buffer. And there's another buffer replacement policy which I'm gonna skip in lecture. You guys gonna read it yourself. It's fairly straightforward. Just read the slides, you understand what's going on. So I'm gonna skip this. We talk about the difference between buffering in database management system and buffering in OS system. So I'll skip that. Now we come back to disk-based management. So we understand disk, and we understand buffer, but we haven't talked about the disk-based manager in detail yet. Now we're going to come back to this and try to all right. Yeah.
I was just going to make a comment about the OS page buffer versus the database. It also seems like you maybe want to have a separate buffer because you're kind of managing what is mapped inside of your address space, like inside of the UVMS processor. And you can imagine like if you're using files to store like operating system files to store your data for the database, and you're like memory mapping those inside of your UVMS, that if you map the file individually, that could take up a lot of space, and so it'd be better to kind of map individual chunks of the files.
So I'm not sure I get your question clearly. So let me try to rephrase what you're saying and try to give you my best response. So the biggest difference is from OS buffer point of view, DBMS is a black box.
Right.
So it cannot differentiate a different transaction and thread within a DBMS. Rather, it's viewed as one single black box requesting these pages. So if you think OS buffer management to manage, that will be not as effective as you do this within the kernel, because within the kernel you cannot now you can distinguish between requests from different transactions and so on and so forth. And so you can do a better job in figuring out which is hot, which is cold.
Right.
But from OS buffer point of view, all of this belongs to one thread, which is the DBMS.
Right.
So it's much harder for the OS buffer to figure out what is hot within DBMS and what's cold within DBMS.
But the DBMS, like, it doesn't have, I mean, maybe, does it have control over, like, does it tell the operating system, like, don't swap these pages to this? Does it have that much control?
Well, it cannot control OS buffer. Or you can kick out a page, say a DBMS buffer, but that content might well still be cached in the OS buffer, which DBMS has no control of.
Right, right. Yeah, so it seems like it's the mapping, like it's controlling like what's remapping.
Oh, the DBMS doesn't try to manage OS buffer. Right. So if it gets a free write from OS buffer, why not? You leverage on that. You get if you do get a free write from the OS buffer, why not leverage that?
Yeah.
But if there are some other competing thread running at the same time, then too bad.
Yeah.
Okay. But at least I can manage my own buffer space.
Yeah, like what's mapped.
Yeah, but if I do get a free write from OS buffer, for example, no other thread are currently running on my operating system, and my DBMS is the only major thread going out, and even if I kick out something from the DBMS buffer, it may still be cached on OS buffer. Fine, perfect. I mean, that only improves my efficiency.
Yeah.
I could not be happier if that's the case. If you are the DBMS, of course. Right. Okay, all right. So let's come back to this, and I will do another quick demo. If you saw the discussion I had with Charlie on the Canvas website, I promise you I want to show you something in Postgres SQL, which actually precisely solves the problem we have just seen, which is what happens if a two-table join takes forever to finish. What do you do? Okay, and we have a system to address that. We'll show you quickly in a minute if I finish this. So this statement, I've been having this coughing problem for a month. No sound getting better. I don't know why. All right, files to records. So in database manager, like I mentioned earlier, each database table is mapped to a file on disk. Okay, and each database record is mapped to a single record in that file. And the file is a collection of pages, and each page has a collection of records. So that's the hierarchy that they follow, right? A file, collection of pages. Within each page, you have a collection of records. Okay, that's the way it is. So, from high-level point of view, a database file must be able to support the following operations, which is to insert, delete, modify any given record, and find a particular record. In other words, fetch this particular record, and scan all possible records, and potentially with some condition on top as well. Okay, for example, find all the CS students. So you are scanning over the student file with the condition that major equal to CS, for example. Okay? So there are two main types of file structure in a DBMS file system. One is a heap file, one is a file. So let's talk about heap file first. Heap file, don't confuse heap file with the concept of heap from your data structure or algorithm class, in which heap actually oftentimes is implemented as a binary tree which is sorted. In database file system, DBMS file system, heap file is really an unsorted file, unordered file. So there's no sorting, no ordering at all. Okay? And to support record level operation that we have just mentioned, to support this operations, we must be able to keep track of, first of all, keep track of pages in the file, and free space on pages, and then keep track of record within each page. So there are two structures for heap file in DBMS. One is to maintain two double linked lists. There's one header page that stores some metadata information about this table. Remember, each table is mapped to a file, so this header page stores some metadata information about that table and the file, such as total number of pages I have so far, and so on and so forth. And then you have two linked lists of pages. And this is the top list is the pages that are completely full. There's no more space for any new record. The bottom list is the list of data pages that have some space for accommodating additional records. Okay, so that's alternative number one. Yes, question.
Two separate interest spaces and empty pages. So if anything goes in the empty page, we have to move it to the.
Yes. So if a page with space down the road run out of space, you have to move it to the other side, and vice versa. If the other page gets deleted, some records, then it will be moved down. However, note that we are talking about heap file, so there's no order involved. This movement is fairly efficient. It's linked list, right? Linked list, you can insert and remove elements fairly effectively, fairly efficient, because you are not trying to maintain any order. This structure is simple and overhead is small because you need all these pages for your records. The only actual overhead is the header page, but you do need that to store some metadata information, but there's only one page overhead, which is not too bad. Okay? However, the downside of this approach is it doesn't support random access to the pages. That's the fundamental drawback of linked lists, right? So people come up with another structure that does support random access to any single page. But then the overhead is slightly bigger, which is for each data page, I make a data page entry, which is the small rectangular box that contains a pointer to that page, page ID, and some minor, really tiny, teeny metadata information about that data page. And this is what I call data page entry. So I'm going to have one such data page entry for each of my data pages, and the collection of the data page entries, I can push them into the directory pages, what I call directory pages. Maybe one page is enough, maybe I need multiple pages, but the bottom line is the size of this, each of the data page entry is going to be much smaller than the data page itself. So even though you have n data pages, which will produce n data page entries, it doesn't mean you're going to need n pages to store these data entry pages. Oftentimes, you need much less than n pages to store these data page entries. Which means these red color pages, these are overhead pages, going to be small, not going to be big. But the benefit of doing this is you no longer distinguish between data pages with space or without space. But the benefit of this approach is now you can do random access. In some sense, you are still doing linear scan, but you don't do linear scan over pages directly. You do linear scan on data page entries, which is much more effective because they are smaller and occupy less number of pages. And you find the data page entry you need, follow the pointer to fetch the data page. Okay, so that's the second approach. Index, I will talk about index later on, so let's skip this. That's how you organize pages into a file. Okay, that's how you organize pages into a file. The next thing we're going to talk about before we talk about how we organize record within a page is how do we organize attributes within a record. Each database record may have multiple fields, right? Multiple attributes. So we need to understand the structure of record in order to understand how things like projection works. So depending on whether you're talking about fixed length or variable length attributes, you may have different organizations. Fixed length and variable length. So remember earlier we said about had a discussion regarding this, right? Chart 20 and the bar chart 20, right? Do you still remember this? And this is where this subtle issue of variable length and fixed length come into the picture. If you have fixed length record, it's very simple. Each record will simply lay out the attribute one by one. But the only constraint is that different records must follow the same order when you lay out your attribute values. That's it. And you store your schema information in a metadata table somewhere, so that database will know where to retrieve the metadata information about your table. In other words, schema and things alike. And once I know your schema, from the schema I know, oh, it's fixed length. The first 20 bytes is name, next 5 bytes is age, so on and so forth. And once you give me a record, I can do parsing without any difficulty and without ambiguity. You follow me? What about variable length? Well, variable length, you can do two things. The first approach is you introduce a special delimiter between values of different attributes, so that whenever you see that special delimiter, you know that marks the end of the current attribute value and the beginning of the next attribute value. And you can do your parsing that way. But the downside of this delimiter approach is, again, it doesn't support random access to a particular attribute value. You have to scan a record from beginning in order to find any attribute value of interest, which might not be a problem if record is small, but for big, long record, this will be a problem, efficiency-wise. You follow me? So that's why another approach is to introduce a kind of like the directory pages we have talked about. You introduce a directory attached to a record at the beginning of the record that points to the offset of each attribute value. That's it. Then with this information, you can easily find the starting and ending address for a particular attribute value within a record. These are drawn as pointers on the slide, but in reality, these are simply offset values. So this will be, for example, 0. No, not necessarily 0, because this will occupy some bytes as well. Let's say each of these occupy 2 bytes, so this will be 8. If this is 10, this will be 18, and so on and so forth. Okay, the offset values. Alright, now let's talk about how we organize records within a page. That's essentially project 1. Okay, records within a page. Again, there are two cases. One is fixed length record. Fixed length record is easy to deal with. And when do you have a fixed length record? When every single attribute is fixed length, you have a fixed length record. If you have at least one record that's variable length, then the entire record becomes variable length. So fixed length record, you can do either a packed approach or unpacked approach. Packed approach basically means, okay, this is my page. I partition my page into slots where each slot is precisely the size of one record. Because I'm talking about fixed length record, I can do this. And I can even calculate a number n, which is the maximum number of records that can fit into a page. Again, this is possible once you know the page size and the size of record, if you're talking about fixed length record. And then I partition my page space into two segments, two areas. One is what I call the record space. One is what I call the free space. The record space are denoted by white color box. The free space is denoted by the solid black box. So in this case, it's packed, meaning that records must be consecutive to each other, and free space are consecutive together as well. There are no holes in between. And what's the benefit of this approach? Well, the benefit of this approach is, if you, this n is not the maximum number of slots you have, but the number of slots occupied by some actual records. If you do this approach, all you need to do is remember one value n, and with this one value n, you can figure out this boundary line very easily. Because again, you are talking about fixed length record. N times the length of one record gives you the offset of that boundary line. And these boundary lines you don't need to remember that because you can figure them out automatically once you know the record length. Okay? You follow me? But the downside of this approach is if you do deletion, you have to do this packing operation all the time to make sure there are no holes left between two records. But the plus side is the overhead is small. You just need one number to figure out the entire structure of the page. The other approach is, again, this is kind of like the directory page or the record. We maintain a directory, and the directory is simply a bitmap. Now this M, capital M, is the total number of slots I have, whether the slot is occupied by a record or not. So this M is the maximum number of records you can hold in a page. Then I maintain a bitmap using 0 to indicate there's no record occupied that slot, 1 to indicate that there is a record in that slot. Then I'm done.
These records are unordered, yeah?
Unordered. They are unordered. Okay, so fixed length is fairly straightforward. What about variable length? None of this will work for variable length, right? Do you follow me? Very simple, because this boundary lines become messed up if you use variable length. Somehow you need to remember each individual boundary line for each single record with respect to variable length. That's precisely what we're gonna do next. Yeah, question?
Hold on, it's saying in the first alternative, moving records may change to RIP.
This N may change, yes. This is the number of records in the page. This N may change over time with deletion and insertion.
But I thought it was unordered.
It's unordered, but doesn't mean the number of records is fixed. You may have 10 records, you may have 12 records in the page, right? N is simply a number to tell you how many records are currently in the page.
But does it change the record ID of the record that's in the slot? So if it moves that record to another location?
Good question. So the question is, will the deletion and insertion change the record ID for a particular record? We haven't talked about this concept of record ID yet. So let's talk about the variable length first, then I will come back to that here, to the fixed length. Okay? Now let's look at the variable length format. Instead of reading through this slide, I just give you this picture. Then we'll go from here. This is essentially your project 1. Okay, so you are going to implement this structure. So pay attention. So variable length is as follows. Again, imagine this is your page. And suppose this is the ith page in your DBMS. Ith page. That's why you see the index I over there. And you partition your page into two areas. One is what I call the record space, which is the area on top, the big white space with some black solid rectangular box. Those are what I call the record space. And the gray area down below, this is what I call free space. Free space, available to hold additional records. Record space are packed. That's observation number 1, even though it was not the case on this particular slide, on this particular picture, because I don't want to draw too many records to confuse you. But imagine they are packed. Meaning that between any two records, there is no space left. Records are fully packed in the record space. You follow me? Now, because we're talking about variable length, one critical observation, as I mentioned earlier, is that you need to figure out the boundary between records. As long as you are able to do that, you are fine. That's all you need to do. All right? So how do we do that? Well, we use the same trick we have seen over and over again. We use a directory to keep track of the boundaries. And that's what you see here. And what we call the slot directory. Slot directory has a couple of key components. The first one is this blue dot here, which is drawn as a pointer, but in practice, in the practical implementation, this is essentially an offset value to the boundary between record space and free space. So for example, and when you talk about offset, you can calculate this in two ways. One is offset to the end of the page or offset to the beginning of the page. Both works. Either way is fine as long as you are consistent in your system what you mean by offset. If you are using offset to the end of the page, make sure you use that throughout the place. If you use offset to the beginning of the page, make sure you use that throughout the place so that you don't confuse yourself and don't create any bugs. You follow me? Let's say we are using the offset to the end of the page, So if I store a value 500, that simply means this particular point is 500 bytes away from the end of the page. Which means your free space, including the slot directory together, they occupy 500 bytes. Starting from the end of the page, you count backwards 500 bytes, that's where your free space stops. If you do offset from the beginning, then it's the other way around. If you talk about 4 kilobytes page, 500 bytes to the end is essentially about 3,500 bytes from the beginning. For 4 kilobytes page, roughly. To be precise, it's 3,584 bytes. 96 from the beginning. 3,596 bytes from the beginning, if you're talking about 4 kilobytes per page. Now, this n denotes the number of slots in your slot array. And after this, from here to here, is n slot entries. N slot entries. N slot entries. And each entry follow the same structure, but having different values. But the structure is the same. What's the structure of the slot entry? It has two things. The length of the corresponding record and the offset value of the corresponding record. In other words, each slot entry corresponds to a record in the record space, in your record space, and has two components. One is the length of that record. The other is the offset to the starting address of that record. And again, this offset, you can calculate this offset from either to the end of the page or to the beginning of the page, as long as you are consistent in what you mean by offset. Do you follow me? Let's look at one example. Slot 1 points to this record and value 24. What this merely means, it basically says that, okay, the length of this record is 24, and its offset is here, whatever this value is. Let's say this value is 700. What that means is the starting address of that record is 700 bytes away from the end of your page. In other words, the address of this record, the beginning address of this record is 200 bytes away from the beginning of the free space.
Are we keeping the relative address or the absolute address in that?
Are we keeping the what?
Like in that case, are we keeping? Can't we keep the absolute address itself?
Well, there's no abstract address per se, right? Because what do you mean by abstract address? If you calculate the offset with respect to the beginning of the page, is that what you mean by abstract absolute address?
Yeah.
Well, that's just the same as offset, right? What's the difference between offset?
I think we don't need to store the offset.
But what I'm saying is offset to the if you define your absolute address as number of bytes is away from the beginning of the page, then it's the same as saying offset to the beginning of the page. These two are the same thing, right?
I'm saying it can be anywhere in the page. I don't need to store an offset or something. I can just point to that. I can just store the absolute address.
Well, we can take this offline, but what I'm essentially saying is absolute address within a page is the same thing as offset to the beginning of the page. These two are the same thing. Right? So offset is basically an easier concept to deal with if you ask me, because when you say absolute address, it's not well defined, but offset to the beginning of the page or end of the page, that's well defined. And it's encapsulated the case you mentioned. Okay. Now let's look at the mistake. This 24 points to that record. Okay, points to that record. This record is 16 bytes and there's offset. Obviously, if I tell you the offset of this is 700 bytes, the offset of this must be smaller or bigger than 700 bytes. How many of you say smaller than 700 bytes? Remember, I'm calculating offset to the end of the page. Must be smaller, right? Because you are closer to the end of the page, your offset must be smaller. If you calculate offset to the beginning of the page, yes, it should be bigger because you are further away from the beginning of the page. So on and so forth. Okay? That's it. Now, let me finish one thing, then I open for questions. Now, Charlie just now mentioned record ID. Record ID, now we understand this. Record ID has two components. One is page ID. You have to tell me which page you locate at. And what else? Slot number or slot ID within that page. So give you an example. In our example, it could be I1, I2, and so on and so forth. So which is I1? Here is some student get confused. Some of you get confused. I1 means, okay, the first record on page I, so it should be the record on top. No. 1 means slot number, not their sequence in the record space, but their sequence in the slot directory. So I1 is this record. Is the first record in the slot entry, not the first record in the slot, in the record space. Do you follow me? So that's I2 because that's the second slot entry. This is the IN because that's the nth slot entry. Now, Charlie asked me, okay, what about insertion and deletion? Will that impact the record IDs? That's the next thing I'm going to talk about, insertion and deletion. Yeah. First of all, insertion is easy. Right? Insertion is easy, right? What do? You allocate a slot, you take some space away from the free space and allocate that to your record. And if you calculate the offset with respect to the end of the page, you decrement this value by the length of your record. If you calculate the offset with respect to the beginning of the page, you increment the value of this by the length of your record. Do you follow me? And you update the slot entry from n to n plus 1, allocate a new slot entry here with the length of the record being inserted. And the offset is what? The offset is simply the old blue value here. That's the insertion. Let me finish, then I answer the question. Okay, because I do want to finish this. That's insertion. Subject to one minor thing that I omitted, because we have to talk about deletion first in order to talk about that one minor subtlety for insertion. But for now, understand insertion like that. Very simple. What about deletion? Deletion is trickier because you may affect other records. Insertion, you do not affect other records. Deletion, you may affect other records. Because insertion always happens at the end of the record. Because record space are guaranteed to be packed. You cannot insert a record in the middle of record space. It's packed. You only happen in the end. That's why you are not going to affect any other record. But deletion is different. Deletion can happen anywhere in record space, and because record space must be packed, it may affect other records. So if I delete, let's say, this record, the length 16 record, what happens? Very good. You have to shift everything coming after it forward by how many bytes? by 16 bytes, by the length of that record. You follow me? So if you do delete this record, what you need to do is first change this value by incrementing it by 16 bytes. If you calculate offset with respect to the end of page or decrement by 16 bytes, the other way around. And move all the record coming after it forward by how many bytes? Again, 16 bytes. Here is one optimization you can do. You don't have to move record one by one because they are consecutive. You can move all of them at once. And you know the address space you need to do the move, which is from the offset of this thing that gives you the end of the record, which is also the beginning of next record. From that offset all the way to the blue value, that's where you need to move by 16 bytes. You follow me? You start from this value plus 16 all the way to this value, that's where you move them forward by 16 bytes.
I'm just wondering though, if you have enough memory, like is it actually necessary to do all this? Because, for instance, with the slot directory, could you just use a single bit to say like whether the record is active or not?
I will come to that in the very next minute. How do you indicate whether there is a record over there or not? Let me finish the discussion of deletion. So you move that. Are you done? Are you done yet? You're not done yet. Because once you move these records, their old offset values are no longer valid. You need to update these offset values. And here comes the most difficult challenge that might not be obvious to you. How do I know what record to update offset values? And how do I update their offset values? This is somewhat trickier because the sequence of the records do not correspond to their sequence in the slot entries. They are not ordered the same way. The record coming after the record being deleted doesn't mean their slot entries are below, behind, right behind the slot entry of the corresponding record. You cannot just go over the slot entry coming after the slot entry being deleted and just update it. Wrong, because these two orders do not correspond to each other. So how do you do it? How do you do it? The trick is, if you look at the offset values, the record coming after this record, their offset value must be smaller if you calculate the offset with respect to the end of page, or bigger if you calculate offset with respect to the beginning of the page. Must be. That gives you a way to figure them out from slot entries. Well, you do a linear scan of slot entries. Whoever has the offset value smaller than the offset value of the record being deleted, what do? You add 16 bytes to it. That ought to fix them to the correct new offset value because you move them forward by 16 bytes. 16 can be any number. It's the length of the record being deleted. That's it. For those guys with offset value less than, bigger than, if you calculate to the end of page, bigger than the offset value of the record being deleted, you do not touch them at all because they didn't do anything, they didn't move. There's no change. Finally, one last thing you need to do. This slot entry is no longer valid. It no longer corresponds to a record, right? So you have two choices. One is you deallocate this and you move everything back. You could do that. But if you do fairly amount of insertion and deletion, why not simply mark this as available? Say you remove the offset value and you set the length to -1 or some pre-agreed default value, so that a subsequent insertion can recycle this slot rather than always dynamically increase and decrease the slot directories. That goes back to the subtle thing I said about insertion. So for insertion, you scan the slot entry, you find the first slot entry that's available for recycle, and you use that. Do not necessarily go all the way to the back and allocate a new slot entry. If there is none available for recycle, yes, then you do what we said earlier. And that's all.
If your new insertion instead of the deleted space, that's a record that's longer than before,
I have to answer a question offline because there's a class coming up. But what you are saying will not happen because we pack the record space. Okay. With that said, you can do your project one. I believe the only difference between the project and this is it's flipped. This is at the beginning. Free space at the beginning and record roll backwards. So that's kind of like a purposely done trick to confuse you a little bit to make sure you understand what's going on. But it's the symmetry of, it's exactly the, if you look, you kind of look at this in a mirror, that's essentially what happens. Upside down mirror. Okay? Not left, right. Okay? Alright, I'm available to answer your question in the office hour or email if you have any questions.